Okay, so I've been talking to other faculty members in the department. Actually, they're really happy that we're doing finite state machines. This is our last day. And we not only, well, actually, this is basically, I took out that one week on number theory that usually prepares students for cybersecurity, which did not work last year. So we put this in, but we actually want to keep this alive. So you might actually see some finite state machine in data structures, those of you moving on to it. Conceptually, not like you don't have to implement it, but that, I think that next year's algorithms class, we may end up implementing them also, make them actually become operational. So yeah, Charlie, what's a finite state machine? I'm just trying to like make sure that we're all on the same page, yeah.
It's basically a machine with a predetermined set of states that you move between by inputting the string.
Yeah. So let's actually be very careful about the word machine. It's not really, like nobody really sits down and builds these things.
It's not physical.
It's not physical, it's an abstract machine, it's an abstraction, yeah. The machine actually is sort of like a concrete example of computation, if you think about it. You say that I'm thinking of this language that accepts these following words are part of this language that I'm inventing, and everything else is unacceptable, like it's not part of it. And you might say, well, that sounds a little too elusive. Like, what do you mean by language? I could say the language of integers, or the language of real numbers, like something point something. And it gets more complex, but it starts there. And so anything that is a meaningful sequence of digits, a single point and some other digits, is the language of real numbers. So that kind of thing. So someone else, let's see, Ethan. Determinism versus non-determinism. Do you remember what that means in the context of finite state machines? You don't? It's okay. Like yeah. If you don't, that's totally fine. So, Jaden.
Determinism is where if you're at a state, you know exactly where you're going to go depending on the input.
Mm-hmm.
Indeterminism is if you could get the same input and go to two different places.
That's good. Yeah. And so basically, I also would have accepted the transition. If it's a function, it's a non-deterministic machine. It's a deterministic machine. If it's a relation, it's a non-deterministic machine. You said indeterminism, right?
Yeah.
That's a word, like in the English language, they actually have non-determinism. Like, I think they subtly mean different things. And I don't know what indeterminism means. I know that it's basically like not deterministic in some ways. But the word specifically is non-determinism. And that's like a CS lingo thing. So what I want to do today's plan is the following, this being the last lecture. I want to show you a machine that actually has a relation for its transition function. And then we will collectively turn it into a deterministic version. And then we might actually realize why non-determinism is a useful thing. And then I'll give you an exercise that you've done before, which is recognizing the word ABBA. But if you remember doing it on the whiteboard, it was neither trivial nor excessively difficult, but you had to think about it. Like, you know, like if I see an A, like where does it take me back to? You will see how easily you could express it as a non-deterministic formulation, and then if you have a mechanism to turn it into a deterministic version, then that's basically the process we follow from then on. So I went back to a book that I studied as a student. It's a good book, so I'll read you from the good book. So this is a theory of computation, and it actually is like 30, 40 years old. And it is, I actually went back to this because when I did a Google search on like meaningful examples, I would say 50% of them actually were like faulty. Like the things that I encountered online actually were not correct, half of them at least. And I like this because I learned from this, and some of the examples are actually just really to the point. So I want to give you something, and then I'm going to ask you a few questions about like, so the first question will be, what do you think will be the strings that this thing accepts? Like what are the valid strings for the machine that I'm writing here? And then we'll go from there. So the state machine is like this. And by the way, after we do this first one, the non-deterministic version of ABBA turned into a deterministic version will be your turn, so you'll work on the whiteboards. So this is state 0, this is state 1, state 2, state 3, and state 4. So then if you get an A, you go to B, if you get to 1, if you get an A, you go to 3, and then an A makes you loop back, and then a B takes you here, and then a B takes you back to here if you're already there. So C takes you here, and A makes you spin there. And this is a C. That's a final state. That's a final state. Let me make sure that I got this. Like, so 2, 4, 1, 3, 0, A's, A, B, C, and the transistors are B and a C. Okay, yeah, so my first question, what do you think is the set of strings that this thing accepts? It would also be cool, like, it's unfortunate that we have half the class here. Again, that makes me feel actual pain. But for those of you who are here, let's make it worth it. So for instance, if you don't understand like something, and if you haven't understood it on Monday, Wednesday, and Thursday, you really have the right to ask still, like, I don't get that. So is there anyone who wants me to talk about any of this? May I assume everyone's 100%? Okay. Yeah, so can you tell me like what might be a string, one string that this thing accepts, and then we'll generalize from there. Yeah. AABB, so let's see, A, B, final state, it accepts it. Miles, you give me one?
AC.
A and then C, okay, that seems to be fine. Can I have one that doesn't work, like something that is not an accepted string? Yeah.
BA.
Yeah, because I don't know what to do with this one. In fact, I was gonna say, like, as formalism, do you think that this actually is a legitimate finite state machine? So 2 people are saying no, that's great. 3, why is that?
Because most of the nodes don't have like relations for all of the possible inputs.
Yeah, exactly right. And I would say that this is actually a function where not every domain has an arrow coming out of it. You don't know what happens if you are here, you get a B, which is what you said. I guess that's one thing we have to address, because this is basically, I could see the intention. Someone was so consumed by coming up with the strings that are accepted that they forgot to add the transitions to indicate what happens when it's not accepted. But there's something else to be noted here. I want to have other people chime in hopefully. So Rohan, maybe? Like, is there anything here that kind of bothers you?
2 doesn't go to, like C doesn't connect, so you can't have ABC string.
Yeah, I mean, you are right. Like, you know, there are certain things, strings this is not supposed to accept, but that is not made clear. But there's something, so like, I don't know if you know, like the first example I got was AABB, and then we said that's accepted. Then the next one was ABC, that was accepted also. And I had to exercise some intelligence here to interpret both of them. Like, yeah, well actually, Janet.
Well, you don't know which way you're gonna go with the A.
If I get an A here, I don't know where to go. So I'm beginning to understand what whoever designed this, the author, by the way, it's theatrics, I know exactly what's going on. So they're actually making us realize these things. So let's start by saying, is there a way for us to concisely represent the strings that are accepted here? And I'm going to do something like this. Let's see if that makes sense. This is not complete. I'm just hoping that you start to make like sense of it, and then I'll make it formal. So does anyone know like what that gibberish means? Yeah.
I think it means like the first character has to be A,
Yeah.
and then it has to be A at least once, and then repeating more times.
Well, the first one actually is A is the at least part.
Yeah.
Like I get one A, and then I can actually do this
Like
0 or more times.
More 0 over times.
So I have guaranteed that there's only one of them here, and there's also one. So no matter where I go, it looks like I'm going to consume at least one A, and then some other number of A's, and that some other number can be 0. And then you transition into a B,
Which is this.
and then you have some number
0
of B's.
or
It could be 0. So what I'm doing here is that this is called a clean star, KLAIEIN or IEN, doesn't matter. But so basically this is saying 0 or more. It's an exponent. And when you have, this is again an operation that's being overloaded. So when I say this, when I say x squared, if x is 10, you say that's 100. That's what we have been conditioned into it. But now you can actually overload the meaning of an exponent. So we did that, for instance, when you are doing transitive closure for relations, the second power is actually the composition of the relation with itself. That was not squaring things, right? So you see one more example of the exponent being generalized, and that just means 0 or more of these things. Those of you who are more programming, sort of like interested in CS, you may have seen things like this in regular expressions in Python, in C, in C++. Every language actually has this, which indicates a pattern of strings you're looking for. So what this means is start with an A, and then have some number of A's followed by at least one B, and then some number of B's, and I'll accept that. That's actually fine by me. And this one says, I also am accepting at least one A followed by at least one C, and as to which one, I accept them both. So this is what you can do. We can actually have a little bit of notational things, so we can do this. So star means an exponent that's at least 0. Plus means an exponent that's at least 1. So this being the 1, I could say A times A star is actually A plus, B times B star is B plus. So this is basically any string that has 1 or more A's followed by 1 or more B's, union with all the strings that are some number of at least one A and then at least one C. Okay? Now, this is actually a monumentally important thing that I have not had the chance to say to an audience at IC for 20 years I've been here. This is a machine. It's a finite state machine. Its purpose in life is to say yes or no. Its purpose in life is to say yes or no to candidate strings. Like, you're one of the ones I'm looking for, or you're not one of the ones I'm looking for. This actually is it recognizes whether the input was accepted or not. This is a generator. This one actually is a way to generate particular types of strings. So that would mean that anything that is produced by this description will be accepted by this. And any string that this is unable to recreate will be leading to an unaccepted edge rejection. This is like probably, if I were to come up with like 3 pillars of computer science, this is it. So that would mean that, for instance, when someone, like in the 2000s, they came up with Python, they actually wrote a bunch of rules that determine what are legitimate strings that constitute valid Python programs. So that's basically the grammar of the Python language. And then you write a Python compiler like your, what do you guys use in CS1 and CS2? The PyCharm, is that it?
Yeah.
PyCharm. Yeah, basically this is PyCharm. That it takes someone's text and says, if you have followed these rules, this is going to be a legitimate Python program, and I will be able to execute it and make it do whatever it's meant to do. So, and this is like, this duality is a thing in computer science, that you have a mechanism to generate strings that are meaningful, and then you have a mechanism to detect if a string has followed the rules of the generator. Really, really important stuff. And because we are so practically oriented these days, that these fundamentals don't get mentioned, so here we are talking about it. Does anyone have any questions about this? Yeah.
What happens, or I guess can it happen, that you get the first A and it goes to the top row, and then you get a C and nothing happens? Like, will a C like AC always go to the bottom row?
I think that it needs to have the string terminate at least with a B or a C.
Yeah, but like,
But you
how
can't
do
have a
you
mix of
know
them.
what if you're gonna get a B or a C next with the first?
Give me a string.
Like ACC.
ACC, so it takes me here, and then CC, it's accepted.
So it'll never go to the top half?
Well, that's the non-determinism part.
Oh,
Like,
okay.
Right? I mean, you have to kind of like, and this is what I did. Like, again, I used my human intelligence to try to figure out what you guys meant when you said AABB will be fine, and then someone else said, like, I forget who it was, AAC, and then both accept. So I had to say, oh, I bet this is what they're thinking, or I bet this is what they're thinking. But then the machine doesn't have that intelligence, right? So this is what I mean by that. Non-determinism makes it easy. Like this union, I'm interested in A's followed by B's or A's followed by C's. That's a rule. This machine just says, sure, let me mimic what you wanted. But then when you see a string, how do you know which path to go? Okay, so moral of the story, yeah.
Well, sorry, I was just gonna say, is it like an OR operator?
It is. Yeah, exactly.
And why couldn't it be an and?
And that's basically when you make it an and, I think that the or is applicable, and is not. Or is like you go this way or that way, but then and would mean you go both ways, and that's not what we are looking for, because we really have to go one path to figure out if it leads to an accepting state.
So it chooses one path based on the, so it would choose A, B if there's an A and a B in it, and then it would choose A, C if there's an A and C.
Yeah, so what you're doing is now you're saying that maybe I won't need to see the whole string, but I need a little bit of look ahead to
Yeah.
figure out which way. And you could do that. But what we are going to do now is we're going to get rid of the non-determinism, and the process is actually quite remarkable. And then that process will produce a deterministic version of this, and we'll say, oh, this is how you would have done, without any of this kind of clever way of thinking. So first thing I'm going to do is this. I'm going to take this, and by the way, this is remarkably also moving into territory of Comp 311, because this is what we call a graph. Like you have a bunch of interconnected things. The semantics are different than what we usually consider graphs to be, but it really is a graph, interconnected things. And every graph can be written as a table. Do you have a question?
Yeah, can you explain what the plus means again?
At least once, at least once. So for instance, if I had, like, if my pattern of strings was 0 star 1 plus, that would mean that I'm thinking of strings like this: 0 0 0 1, or 0 1 1 1, or 1 1 1, because I exercise my right to have none of this. The star allows it to be 0, but then this would not be an accepted string because it doesn't have at least 1. So this means an arbitrary number of, with the exception that star means 0 is allowed, like you don't have to include it, but this one I need to have at least one of them. Yeah, yeah.
This is unrealistic for like way the bigger scope, but could you just like say it goes through both paths like in your head, and then like see each path like if it works or not?
I think for every practically relevant language, that would be like overwhelmingly difficult.
Yeah, exactly.
Yeah. But yeah, I mean, by the way, this is really getting into, like, let's take this offline. Like, I want to talk to you more about this, but you guys know about Alan Turing? Has anyone heard of Alan Turing? Really a foundational guy for computer science and mathematics, and he actually was kind of like talking about, this represents computation, by the way. Like, this is just computation rendered in some visual form. And he was saying, if I were to permit me to pursue multiple paths simultaneously, does that actually make computation become grander? Can it calculate things that the deterministic version could not have? And one of his most substantial findings is that it doesn't. Again, this is like gradual level of computer science theory, but the guy was basically figuring out the boundaries of computability, which for those of you who might be interested in space, you guys know that there's this basically visible universe around us, and there's no way we could see beyond that because of the speed of. So Turing was able to figure out the sort of computability space that we exist in, indicating that there will be certain problems that we simply will never be able to solve because it is beyond that boundary. He came up with it. It's called the halting problem, and there are YouTube videos about this if you want to look it up. Not right now. It's very similar to like the diameter of the visible universe being like 90-some billion light years, and there's stuff beyond it, we just can't get to it. And he was able to come up with something analogous to computation, that if you're within that space, there are multiple ways to calculate things, but then beyond that boundary, no matter how smart we are, no matter what AI you have or anything along those lines, they are simply unsolvable problems. Yeah, and it was sort of along the lines of what he said. So what I want to do is I want to turn this into a table, and the table is going to look like this. I'm going to have my states here, so I have what's 0 through 4, right? 0, 1, 2, 3, and 4. And then I'm going to have my input here, A, B, and C. So this is, again, it's interesting in the sense that the information content of this and the information content of this will be the same. So different formats, but they're able to convey the same exact meaning. So if I'm at 0 and I get an A, I could be either in 1 or 3, so I'm going to represent it as a set of places that I could be occupying. Jesus Christ, I can't do 3. I think that I'm actually kind of like, every time I have to do a brace in a lecture, like I can't do 3s in that lecture, like they just, 1, 3, close brace. Yeah, there you go. So then 0 doesn't know what to do with B, 0 doesn't know what to do with C. Okay. Now 1 gets an A, goes back to 1, gets a B, goes to 2, doesn't know what to do with a C. Check my work, please, because I always make mistakes. So here, so if I'm at 2, if I get a B, I go to 2, and A and B, A and C, we don't know what to do with. At 3, if I get an A, I'll go back to 3. If I get a C, I go to 4. And then if I get a B, I don't know what to do with. And at 4, basically C takes me back to 4, and I don't know what to do with any of the other inputs. Did I do this right? Anyone? Okay. Now, can someone actually, before we engage further in this, oh no, you know what? I want to continue, and then I'll come back to this. Like, we need to fix this. This is not a function, and we haven't remedied that so far. So here's what I can do. What I'm going to do is I'm going to write this with a different color now. I'm going to say, all right, but what if I actually was either in state 1 or state 3? So in other words, this subset of states, I'm going to treat it as a new state. It's like you're either this one or that one. That notion is captured in one state. I'm going to say, for this state, that means I could be either in 1 and 3. How do I actually put these values? Can anyone guess? Not the usual suspects, like someone who hasn't spoken yet, maybe. So this one tells me what I need to do if I get A or B or C. This one tells me what to do with if I get A or B or C, depending on the state. I react differently. This one is like you're either in one or the other. So like, how do you think I can populate that row? Yeah.
It's going to be the union of all the possibilities that 1 and 3 can do, so that would be 1.
So this would be 1 or 3, so it's going to actually, it's going to be this, 1 or. Oh. Okay, so it's this, and then 2 and, so that's going to be 2, and then 1 and 3, and then 4 comes here. Okay, so basically I said that kind of like, it's so funny how it connects with physics. Like I could be here or here, the quantum properties of fundamental particles. But then if I'm actually in one of them, basically where I could go next will be the union of the consequential steps. So this is if I'm at 1 and 3, I get an A, I stay where I was. But if I get a B, I go to 2, one of the states that I defined. If I get a C, I go to 4. Everyone good? So let's actually do this. Let's say that I'm going to call this state now 5. That means that this should also be renamed to 5. So what I'm noticing is this is the bottom line, like this is what you take away. Subsets are being relabeled as new nodes. And so if I can go from a set of elements to all possible subsets, you could see that this deterministic version will be a lot bigger, but it won't have any of that ambiguity. Okay, so I want to draw this now. So if I'm at 0, and if I get an A, I go to this new state 5. So if I'm at 1, and if I get an A, I go back to myself. If I'm at 2 and I get a B, I go back to myself. Oh no, if I'm at 1, I get a B, I go to 2. And then at 2, B makes me cycle back. So then 3, if I get an A, I go back to myself. I don't know what to do with B, but I go to state 4. If I get a C. And at state 4, I spin around with C's. Okay, I think I didn't do the whole thing, so let me show. So if I'm at 0, I get an A, I go to state 5. Okay, B and C, nothing. In 1, I go to myself, to B, to the next one, and that's it. At 2, I spin. At 3, I go to myself with an A, or to 4. At 4, I spin. Oh, we forgot this one. So if I'm at state 5, if I get an A, I stay where I am. if I get a B, I go to 2. And if I get a C, I go to 4. And let's also remember that these are the final states. Can anyone see what happened here? Yeah, Mark?
You just condensed the two different nodes into one.
I did that, yes. But then in terms of like how this thing behaves, there's like at least 2 things you could notice. And I don't want to say any hints because I don't want to kind of like ruin it, but yeah.
It's going to the end now, like, it was going to 1 and 3 before, now it's going to 2 and 4.
Yeah, but like how did it, is it, yeah?
Now 1 and 3 like don't have any purpose because they're not reachable.
These just became unreachable for one thing. I actually don't even need to have them anymore, right? But then what happened to the situation where we didn't know if the first 8 takes me here or the first 8 takes me to here?
It's no longer non-deterministic, now it is deterministic.
Yeah, but yeah, exactly. Look, so it says if I get an A, I'm just going to go here, and then I'm going to consume as many as I need to. Then if I see a B, I'll go to a state that consumes the remaining B's. But if I see a C, then I'll go to a state that consumes the remaining C's. This is a function. You don't have non-determinism. You always know exactly what to do. So the relation, this was the transition here was a relation. The transition here has become a function. And now you could turn this into code. Cool, right? Yeah.
So those two, like, representations are of the same thing, but the one on the right we can more, like, concretely turn into something we can use. Can you go back over the table and how you were, like,
How do I-
explaining?
Sure.
how you-
And everything until the blue was I was transcribing the information in this. So I wrote all the states as rows, and the columns were possible input symbols. And then basically if I was here and I get that, I go to the state. So I capture the transition as a table. And then I said, well, there's this one situation that's kind of sticky. If I'm at 0 and I get an A, I go to either 1 or 3. And I consider no longer as a state that I go to, but a subset of states I could go to. And then I said, okay, let me see what would happen if I were at that state. So this, like, what if you are here, and what happens next is the union of what would have happened if you were here and you get the next symbol, or if you are here and you go next. So once I had like this row and this row, this, whatever's in here was the union of these 2 things. I'm happy to explain that, attempt it one more time. Did it make sense?
Yeah, it started to.
It's okay. So is there someone else who may want to actually just basically repeat what I said, but you guys might be better at it? Yeah.
Yeah, can you just explain what the union and the or means in this case?
It's basically me keeping the generality that is expressed in the system. If I'm at 0 and if I get a B, I don't know what to do with it. I freak out. If I'm at A, I get a C, I don't know what to do. I freak out. But then when I get an A, though, there's a different kind of freak out. I could be going to 1 or I could be going to 3. And I say, like, stop freaking out. Just keep in mind that you could be at either of those. So why don't I come up with a subset of states that tells me I could be at any one of these? So that's what this is. I could be at 1, I could be at 3. Now the problem is, okay, so if you're in one of them, where could you be next? So that's, I could calculate this way. Well, I could be at 1. In that case, the next state would be 1 or 2. Or I could be at 3, and the next state could be 3 and 4. I union those rows, and then I come up with this. Notice that this 1, 3 is a set made up of these 2 symbols. This is actually a subset too, by the way, which is this union with this, which is nothing. And this is a 4, which is this union with this nothing. So you basically figured out what happens next if you are in any one of these 2 states. Oh, good? Okay, so 2 things to note, that it was easier to describe the things you're interested in with non-determinism. You know, it's going to be either a bunch of A's followed by a bunch of B's, or a bunch of A's followed by a bunch of C's. But then the system says, okay, how do I make up my mind here? And say, okay, let me run through this deterministic version process, conversion. So you take this and you construct this version, and this one never creates that moment you don't know what to do. Yeah. Now, since I can do this for every machine that has non-determinism, this conversion indicates that while this is more convenient to express certain sets of strings. I should do this if I have to project. This one is not any more expressive, not any more powerful, not any more sophisticated than the deterministic version.
Will it always like make it so that the points that were in the subset aren't needed anymore?
And then that there are cases, in fact, so that's a very timely question. So in this case, like I could actually, as a human, say that there's no way for me to get to these things. I might as well ignore them. But in many cases, that's not going to happen. Yeah, what's going to most likely happen is, if I have, and see, you'll make the connection. So if I say, do you guys remember what Q was in the finite state representation? What was Q?
Set of all the states.
The set of all the states. What would that mean? Bars around it?
Like how many states?
Yeah, it's the number of states that I have. So if the non-deterministic finite state machine has this many states, in the worst case, the deterministic finite state machine will have 2 to the. So it could be quite explosive because you're keeping track of all the places you could be. So you're saying that I'm starting from one set, from one state, and I'm transitioning to a subset of states. So given a set of this many elements, how many subsets does it have? Is this? It's actually giving you a measure of how much bigger this could be. So this was a little unusual in the sense that it didn't display that because this didn't, but then it ended up producing these things. So let's not misgeneralize this, but in general, this is the thing that happens. You go from a finite state machine that has this many states to that many. So for instance, if I had 10 states in my non-deterministic one, I will have 2 to the 10 in the worst case states. That's actually 1024. Massive expansion. But that's the cost of getting rid of the non-determinism. Yeah. This is basically, you know that, I'll go with you 1 second. It's a really cool moment because you know how we do computer science? We spend most of our time on the computer part and not the science part. This is it. This is the science part of it. This is the mathy science part of it, which is really very enjoyable once you get it. Yeah.
I was just gonna say for an example of like when they want to go in, you can just put in the arrow from 0 to 1 when it's B. So you can, or, yeah.
I could do that, but this actually doesn't make me, that's not necessary though.
I know, but I'm just saying like for a machine that would have that, like if, like.
Oh, yeah.
B was the
If
next
you,
one,
in other words,
right.
if I were to change this to a star,
Yeah.
like, yeah, I would do that, okay, yeah.
So I understand you could turn most non-deterministic FSMs into a deterministic one.
Not most, all.
Or, oh, okay.
Every
so-
single one.
Because I was gonna say, like, would there be a use in a non-deterministic one for just sort of true random number generation? Like, say you had, taking a look at that first one we did, if you had sort of the same logic you follow, or.
You made a connection that I don't think is valid. Like you basically said, you're equating non-determinism with randomness because you said random number generation, right? It's not the same thing though. Because non-determinism says you could be here or here or here. Randomness actually doesn't give you any options. Like, so what's the next random number? I don't know. But if I say the next random number could be 1 or 2 or 3, that's a different thing. And non-determinism is that kind of unknown about the future. But this is, without going like into one more lecture, maybe 2 more, maybe a week more, just believe me when I say this, most of the stuff that comes out of my mouth, you shouldn't. But this one you should. Every non-deterministic finite state machine can be turned into a deterministic machine if you are willing to pay this cost, that it could grow this much more. Yeah. Now, there was no reading about this, and I do actually, Toby did share a bunch of things with me that he uses apparently in software engineering to determine like when you're doing a user interface design, like how does this actually factor in? I'm just gonna ask you to read them over the weekend. And that's going to be what we do this. But anyone who wants to do more of this is juicy, good stuff. Like we could talk about this more later outside of class. Yeah, you had your hand up for a while.
I was just going to say, is the reason you can always make it like deterministic is because it's finite?
Yes.
Okay, yeah.
That's exactly right. That is exactly right. In fact, I don't know if you remember this, but when we said that if a set has, do you remember countable infinite and uncountable infinite? Countable infinite was that basically aligns with integers. Integers are infinite, but you can actually say this is 1, this is 2, this. And then there are uncountable uncountable infinities, which is like the number of real numbers from 0 to 1. That infinity is vastly, infinitely greater than all integers. So if your state space is finite, its power set will also be finite, even though much, much bigger. But if your state space is infinite, then the subsets will become uncountably infinite, which is completely unmanageable. So we can only, with the guarantee of this always being doable is that it's a finite state machine. Yeah. All right, so if you understood this, by the way, I want to actually have you work on the next one, which is like, how do you do the non-deterministic version of ABBA? And then what do you do to turn it into deterministic version? I want to say this. I could have done this. Let's make this 9. It's sufficiently far away. Go there if you get a C. This is B, right? So go there if you get an A and C. Go here if you get a B and C. Go here if you get a B. Go here if you get a B and C. And then put a double circle on it. Not a double circle, sorry. Definitely not a double. It's the exact wrong thing to do. And then keep looping here if you get anything else. This is how you make it a function. Every state and the next symbol is determined, and then you get caught in a state that you cannot accept, you cannot escape, and it's not a final state. So this is how you would actually make this a function without changing the language that it recognizes. Oh, good. All right, so would you please move over to the whiteboards and do a non-deterministic version of recognizing ABBA, which is some string of A's and B's, and you're looking for seeing if ABBA is in there as a substring anywhere. You sound like crickets when you try to open the caps. Does anyone want markers? I have a few extra here.
So we need to make it non-deterministic from the deterministic version? Sorry, do you want to do the drawing? I guess it starts the same way. Almost everything. Right? Or
Yeah,
we have
I
A
think
going
so.
on both.
I think yours.
Yeah. Not really sure what's open there.
Because then if it's.
The top one could be. Or wait, that is the bottom one. Right. So it goes
Oh,
to B,
that's
if it's A, like.
From the starting state.
I guess I'll remove it.
From any of the states.
In about 2 minutes, I want to compare your non-deterministic version so that once we agree on what it looks like, you do the conversion on the same object. Just 2 minutes.
So is it like any number of these or is it specifically?
But it doesn't have to be the
That's
also A.
Why don't you want to write it? 'Cause I'm just having trouble thinking of it right now.
Oh, I
That
see,
doesn't
I see.
work.
We're pretty much gonna set it up at the beginning of the exam.
This one, we're making our
Hmm?
own deterministic version.
You have to come up with a non-deterministic finite state machine that's recognizing strings that contain ABBA as a substring in it
Yeah, but we're converting from the deterministic.
to a deterministic version. But we want to see, like, what does your non-deterministic version look like in the first place? Like, in 1 minute, we'll check that.
It might be easier for you.
Are we going?
If you want to just walk,
I was gonna say, are we going for this or kind of keep making our own?
you're making your own, yeah. And if you want to just join a group and simply listen, that would be cool too.
One more, but how are you
And then
managing?
we'll do this.
So what would they both be like?
Yeah, because it's if we get ABBA, we don't wanna see it if it's
Yeah, if it's at A, then it just stays.
So I should just write one.
That's.
So, and then what would this be?
Oh.
If you're not to do
It doesn't matter.
We need the same thing. So this would be A as well.
If you get like these, and then the next thing
And
back
then-
here, and then you could say it's like this one, you get two of these in a row.
No, it doesn't
Which,
Because
it's not deterministic.
No,
this
if
has
it's
to
a
go
B,
back as
it stays at itself.
intuitive.
And if it's an A, it goes back to there.
That's what we're trying to do two Bs.
Yeah.
A, B, B.
Yeah, but if we have an A in the middle, it'll
That
just
kind
cut
of
it out.
means-
Maybe. So if you get like a B, A, it stays.
And which one?
This would be A. It just has to be, like if it's a B, it just stays your.
What?
Yeah,
No, it's not at any point it's gonna stay there.
But
There's
then,
nothing that's gonna stay there for, because then you have three B's, you got five B's. Yeah, so it's not circling back for any.
if it's an agent,
It goes back.
So what does have to say?
But then it goes forward.
Yes.
Okay, okay,
Then I-
that part I understood, okay.
should we make like
Just do it.
Oh, yeah, you can have it come back together, yeah.
You at least got one spot.
Yeah,
Oh,
because one is two unless you have two, like, or you get an A. The only way to hire this system, you can't really visit it, but has two identical paths that.
Yeah, and then you could have it go to 6.
Because if you have the states to actually hold on to what specifically.
Well, why don't we just say like, so are you saying that it is possible? So, have her come back with it.
But in the end, yeah, I think it is just like a true and false.
And then it's like stuck in there.
Well, is this just like one example that we
Yeah.
do? Like, either go to
To computer grade, I can't do it, I can't do it this weird way.
If there are multiple final states.
3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. Does anyone have the non-deterministic version? So you guys have something? Yeah, what do you have?
We had two different ways of doing it. At first we had states 1, 2, 3, where an A would bring to the second
Sixes
state,
need to
and then
go-
you would just stay there
Okay.
until you got
6 is gonna need to
A,
go
B, B,
back
and
if on.
then I realized, and we just use this as the starting state and say,
So then
until, like,
A, B, B,
you're staying here until.
Yeah, so 6 is gonna go back to
and then you
0.
go to the final state.
The star actually makes it look like you could be like A, B, B, B,
No,
A is also
B.
accepted by this one,
Yes.
Yeah, exactly.
which is wrong.
Yeah, you'd want two.
You must have to.
Oh, cause they're not done
Okay.
yet.
So is there anyone, actually, I'd not want to hear the rest of you. I only have one more and then I'll give you what I think and then so you can attempt the translation. So is there someone else who wants to, yeah, what do you have?
I don't know if it worked or not, but like.
Oh, yeah, and then the 1, 0, and the 7 are you.
Go to
Yeah.
one if it's A and you just leave it back if it's B, and if it's B twice instead of A, you go to C, so it's like 3.
You're still unintentionally trying to make it deterministic when you do that.
Yeah.
So here, guys, like the reason why we do the non-determinism is not to introduce randomness or chaos. It is to make our lives easier. Watch this. So I'm starting here, and let's call the state 0, right? And then I will go back to the state if I get a bunch of A's and B's. I'm just basically consuming the string pointlessly. Now, if I get an A, I go to state 1. If I get a B, I go to state 2. If I get a B, I go to state 3. If I get an A, I go to state 4, and then A's and B's and consumes it, and this is basically the accepting state. That's the non-deterministic version. How cool is this, right? Like, so initially you're saying that there will be a moment where I will encounter the very first A of ABBA. In that case, I'm gonna go this way. But then until that moment happens, I'll just waste the symbols here. Now the non-determinism is, how do you know the next A that you got is one of these or that one? And then by the time you see that first A, you just insist on going here, right? And then you see this 4, and then you spin to consume the rest of it. This is the non-deterministic version to recognize ABBA. Yeah. Anywhere in the string there's an ABBA. Yeah.
What if I get an A, I move to state 1 and I get another A?
This one takes care of it.
No, in state 1, like if I get an A
Yes.
and it ends up taking.
So you
But
wait.
it
No. You got 2 A's, right?
Yes.
Yeah.
So it just stays in 0, cause it's non-deterministic, so you
Oh.
choose, like, you just loop in 0.
Oh,
It's
you-
insanely
you can-
powerful.
You can't say that.
Yeah, so the thing is, like, it's almost like you should see how this movie ends before deciding where it should have gone. This one says, like, I'm not gonna, like, the determinism process will take care of it, but this is enough to express what I wanted. Yeah.
If it's an A and a B, why doesn't it stay?
If it gets an A and B, right? It gets an A and a B, non-determined, like, basically, that's not a final state, so I don't accept it.
So it'd just be like an infinite loop, otherwise, so then instead it just goes down.
But is your string only A, B, or there's more stuff? If it's only A and B, like I stay here or I stay here, in both cases, it's not accepted. But if I get like A, B, and then an infinite number of A's, I could actually say that A, B, infinite number of spins, not final state. It's kind of like it's annoyingly good. Like, how could this thing actually captures what we wanted? Now, if you attempt to turn this into a deterministic one, it's going to look very similar to what you guys had to do last week. Yeah.
So,
or earlier.
okay, I guess this is the part I keep being confused on. It's like, it's not moving by each character in the string, it's looking at the entire string before it goes.
It's actually looking at individual characters.
How's it?
But if you, so this is like, if that actually is enough, so this is not an assignment, but I ask you please to turn this into a deterministic version and you'll see how it works, the deterministic
Okay,
one.
but I don't understand. So if it's looking at each individual character, so we get an A.
Okay.
And we get a B. It would look at A. Why wouldn't it just go around 0? Like, I guess I just don't understand that part. I don't understand.
Actually, almost like you're annoyed.
Yeah.
A little bit. You know what? That's a good thing in this class. So watch this. So I'm at 0, right? I could get an A or a B. So if I am at 0, I get an A. I could be at 0 or I could be 1.
Yeah.
And if I get a B, it's undetermined. Like, basically, I could do this. I could have a fifth state and all the. Well, actually, you know what? I'm not even going to do that. This is good enough. So then I'm at B. I'm at 1.
If you get a B, wouldn't you be at 0 no matter what?
Yeah. No. I just abort. I'm not going to do this. I'm just going to keep only that. So if I'm at 1, I get a B, I go to 2. If I'm at 2, I get a B, I go to 3. If I'm at 3, I get an A, I go to 4. At 4, I go to 4 no matter what. This is also a final state. And then basically this is where that blue stuff starts. So if I'm at this state, 0, 1, and I get an A. So 0 takes me to 0, 1. And then 1 takes me to nothing, but also could be going to 2. So then if I am at, what time is it?
48.
48, okay. I wish that it hadn't ended this way. I think I actually do need that error state here. And then this is going to produce the one that I want to show you. And 2 minutes is not enough for me to do that. Let's do this. So I have like the next hour free, but I'm getting ready for algorithms. In the afternoon, I'll actually finish to share it with you. Then the noise will go down, happiness will go up. Okay, but believe me, the only reason it didn't work is because I just couldn't do it. Like this is like 50, 60-year-old mathematical history, so it's gonna work. I have total confidence in that. All right, see you guys. By the way, I did take attendance. So what's gonna happen is that I'm gonna send an email which contains like how many, like each person, how many days they were present today, because I have photos and I did jot down notes here. And if it's wrong, let me know. But that's going to be how I keep track of people who are actually here this week.